Hi, this is Rashid. Welcome to my channel. Today we have another very interesting topic. I know we are on CMOS, and especially the last part of the CMOS is transistor scaling. Transistor scaling is such a big topic. Trust me, even if you read through that, summarizing things for each technology are very difficult. I found that very difficult at least. And I'm so happy that I've started documenting this. So today, another very interesting process node, 45 nanometer, and then follow on a 32 nanometer 2 years later. So I'll talk about that in detail about those. But first I thought let's do a recap in terms of approximate years. The reason I'm saying approximate is um, technology comes a little earlier. Intel is going to do first test chips to path clear, to test everything, to test production, to test yield. I'm not even talking about the initial, all the lab work, all the readiness that they do for the technology. But test chip comes, then after that, they go with the actual design of the processor on that technology, and that also has several steppings before it goes to production and then released to clients, finally to everybody. I mean, initially it was released to clients as a testing vehicle too. So when technology starts, when actually, it can be a different way. Different people can have a different definition of the year of that technology. But anyway, I just pick some of them years which were in the papers, as well as when the first microprocessor on that technology was released or introduced, just for you to get an idea of which technology came at what time. So 500 nanometer, think of that 1990. 359.35 micron or 350 nanometer in 1993. And I thought, okay, I need to complete this processor list. I think that would be very useful. But I thought, okay, even for people just to understand a higher level, okay, that was the first Pentium game. And that was as 60 megahertz, right? And 3 million transistor in that. Then every 2 years, we have a new process technology. Maybe in another video I will discuss the tick-tock process. One is where new architecture comes, and another one is where technology enhancements come, because you don't want to bring in completely new architecture and complete new technology at the same time. So that tick-tock was very successful strategy for Intel for a long time. So then this area was a traditional kind of transistor scaling. It's called Dennard scaling. Like, okay, make the transistor smaller. When you make transistor smaller, the thickness of the oxide you make smaller. And then you can adjust the threshold. You can reduce the supply voltage, increase the threshold voltage, compromise against power and delay. And net, what you get, 0.7x. You remember that factor? 0.7 is a really key factor. Transistor process technology goes down by 0.7x. That means area goes down by 0.5. And why this number I explained in the very first video of transistor scaling. And the density doubles. Number of transistors becomes, area gets half. Yeah, number of transistors get double, density gets double. And then the performance delay decreases by 30%, frequency increases by 50%. So those are some of the things, but it was with a natural kind of gate length change, and then adjust everything around that. Okay, and then we started seeing that 90 nanometer, you've seen last time we discussed 90 nanometer for 65 nanometer. Okay, new technology came. Here strain engineering came. First generation of strain came. Now that was new thing, which was not done before. And from there, now transistor gate length started slowing down, and we have seen that the gate oxide thickness started slowing down. So it's very interesting. Okay, how to keep going with and keep following Moore's law and keep producing number of transistor 2x every 2 years so that it's still economical for the companies to put more functionality on the chip for the similar size and keep bringing new and innovative devices. Okay, so in 2007, 45 nanometer, another very important technology that was introduced by Intel at that time, and another version of that in 2009. So we are right now in 2009 and all the way to 32 nanometers. So today's video topic is 45 nanometer and 32 nanometer. Just to give you a recap of the past one. 130 nanometer, I consider that, okay, 500 to 130 nanometer kind of traditional scaling. So gate length, and as you can see, the 130 nanometer was a process node, and the smallest gate that they were able to make 70 nanometer. But keep in mind, you don't have to use 70 nanometer device for all your chip. It's really for the very core where you really want to enhance your performance. But as you know that, okay, if high performance comes high power, so majority of the functionality you don't need on that transistor length. Still use 130 nanometer, but you use a different shrink factor within that process node. Gate oxide thickness, that's where it was getting very interesting. And Intel started introducing the concept of the contacted gate pitch. Actually, that was introduced a lot more here. You will see why. And number of metal layers. 90 nanometer, okay, boom, 70 nanometer down to 45. 65 nanometer, you see that? Slowed down. Here is the major factor that was causing that slowdown. You see, this was not changed. And that is really the thing that they addressed on 45 nanometer, which is the next one. But even on contacted gate pitch, overall density was reduced because you have to get that 0.7x type of shrink every process technology, and that was achieved. But now there was more stress on how you can, the goal was for the same area put 2x transistor. So I said, okay, if we can't scale the transistor that much, then what if we still keep the density high by this? And we will talk about this more. I think I gave an idea of contacted gate pitch, what is that the last time, but we'll talk about that again. All right, so today's 45 and 32 nanometer, this is the key thing, gate oxide. So we have a polysilicon gate and 1.2 nanometer T-ox gate oxide thickness. 1.2 nanometer, if you look at what's the diameter of one atom, you really come down to almost 5 atoms. So really 5 atomic layers between the gate and the channel here. The problem that started happening was these electrons which were here, they're starting tunneling here and be present on the gate. And that current leaking here was a problem. Was a problem for power, for heat. So if you reduce it further, that thing will increase. So you really, that original idea of an ideal insulator was no longer existing, and this was not possible to bring this thickness further down. Also think about this. We always think of electron as in a classical physics, like a balls, and they are just bouncing back and forth. Okay, it is quantum era now. And it's very important that we understand things from the quantum side, that when we say electron in an orbit, that means there is a high probability that electron is there. So electron present somewhere is literally a probability. You cannot pinpoint the electron will be exactly there. So another way of thinking of that, okay, there is a wave of electron comes, and that's pretty high probability that electron is here, because this 5 atoms electrons wave can easily go there. All right. So that was becoming a problem, and this was an interesting thing that in 1960 that thickness was 100 nanometer, and in 2001 it came down all the way to 1 nanometer. And compared to the previous technology, if you think of in like a 45 compared to previous one, you're already seeing a 10x 100x more tunneling. So you really think the scale of that was not a small, it was a huge problem. It was just not possible to reduce oxide thickness further down. So when we talk about 45 nanometer, here is a very good paper. They explain everything in a very nice way, and these four gentlemen, what a service they've been doing to Intel for so many years, and I've read so many of their publication and research papers. The technology guys at Intel, from left to right, okay, Tahir, Kezad, Robert, and Mark. And this paper, if you search it, it's available for publicly. You basically, the next few minutes I will give you an overview of 45 nanometer high K metal gate type of story. That's really based on that paper. So you will have a lot more details if you read that paper. But I'll give you a little bit higher level quickly in few minutes. So if you don't have time to read that paper. So look at the traditional case. Traditional case of so far up to 545 nanometer. We have a gate that we call the poly gate, polysilicon. Okay, and for NMOS, this had we made it an N type. So it's like a polysilicon, a single crystal, what you call it, crystal lattice, very pure, but you still make it an N type by adding some purities. For NMOS, we always think it was the same sort of poly, but it was a different poly for NMOS. And for PMOS, because everything, the channel is made of holes, you need to make it all PMOS because you really want to have positive charge here and negative charge. Now for that, you have to make it like the N type and P type. So basically, we always, for NMOS, we had a little bit different gate. Then we had a dielectric silicon dioxide, and this thing together was called a gate stack. Underneath, I didn't draw here, but you had a source and you had drain and you have channel here. Now, goal of this, now all this thing for eventually they found a high K dielectric and the metal gate. That's really the end of the story. That was the main thing in 45 nanometer. But it's not like, okay, they finish one process node and then they start looking into it. Things always happen in parallel in labs. What potential new atoms? You are already looking into next 4 or 5 years potential options. And when it's the time to now go into production, you take the most promising technology in the lab and turn it into production. I mean, fabricating millions of those devices is one thing, and doing a test chip type thing where you need only selected number of chips is another thing. So how you design, how you fabricate is a completely different story, and you need to be prepared for a lot more things for the production case. So first thing was, okay, we cannot live with silicon dioxide, we cannot scale it, we have to keep scaling. We have to bring this capacitance more and more. Okay, what are the alternate things? And what are the properties of that alternate thing? The properties are, okay, one second, yeah. So this thing needs to have a good electrical characteristics. See, the whole point is you bring positive charge here so that it can collect, for NMOS case, a negative charge here. So this thing need to have properties such that atoms within this orient themselves in such a way that there is a high impact of this positive charge over here. So whatever dielectric we pick shouldn't just be just a dielectric. It also needs to have an ability to have effect of strong positive charge here on the electrons here. The first thing. The other thing is, eventually this thing needs to be manufactured. It needs to be in very large quantity. So the manufacturing process, when you put that dielectric here and that gate over here are polysilicon, they should work together too. It's not like, okay, on its own it has very good characteristic, but when you put a gate with it and channel underneath, then it doesn't work. It needs to give first on a previous technology same characteristic that Intel had with the 65 nanometer, but then we are able to control it such that it gives an additional performance out of it. So it shouldn't slow down the channel, it should have increased electric fields there. Third thing is, need to have high capacitance. So what is high K? This case, okay. Think of this. I took a picture from that paper that earlier mentioned on. So two materials, let's say they have a same thickness of hair. The one with high K means two things. So think of this material as K is 1 and this is K is 2. So K2 means it can, for the same thickness, it can have a lot double the number of charge capability. Or if I increase that gap relative to this one over here, it will keep the same charge. Right? For the same material, if you increase this thickness, the number of charge will be reduced because capacitance is reduced. So high K means is better, more capacitance for the same thickness. That's really high K means. So whenever now I use high K material, air or vacuum has a K is equal to 1. I think K is equal to 4 for silicon dioxide. So we need to find a material which has lot higher K than silicon dioxide. So how it all started? Finally, well, actually not all started, but how it all ended. That paper I mentioned earlier on, it gives you a story, how it all started, through what kind of problems and issues they had, and eventually the two materials that they found were most promising were these two, high K dielectrics, hafnium and zirconium. Hafnium is, I think it's HF, hafnium dioxide. And out of these two, this was which was eventually used by Intel. Okay, but finding the dielectric high K was half of the battle as mentioned in that paper. What they found out was when they used that high K dielectric and put on top their usual polysilicon gate, there are problems. The first problem was that in order to get that similar current, the threshold voltage increased quite a bit. And you know that's not good for performance. Remember VGS minus VT, where VT goes up, your VGS still same, your difference gets smaller, the delay is proportional to ID is proportional to VGS minus VT. This is called the overdrive current. In linear case, it's a linear relationship. In saturation, it's a square relationship. And if you increase your VT, this overdrive gets smaller, so current decreases. Another problem, current, not only because of that, but even for the same threshold, current is much lower with this type of combination. And the reason for that one was the second thing that I mentioned here. And it's written in the paper too that what we have these objects, the kind of charges in the form of dipole. So there's a positive charge, so it gets positive here, negative here. This orientation is actually enables the negative charges here, and it is an important factor for the material to be high K because it has this dipole type of structure. But when this polysilicon, and keep in mind the density of electrons is much lower in polysilicon compared to, let's say, a metal, copper, aluminum type. I mean, those are conductors because they have so many electrons. In case of polysilicon, there are not many electrons. The density is low. The problem they found that, okay, when you have a low density material here and this thing is vibrating, what happens is this thing, I mean, this starts vibrating because there's a low density. It cannot keep these from not vibrating. What happens is these vibrates, then the electrons come here, see, with this negative kind of a push. Just they go back here. Or even if they go there, they have to face this force, so electrons become slow. So they realize, okay, thing is not going to work. Okay, found dielectric, but this polysilicon is not. All right, so finally, so I'm giving you the end story now. Finally, Intel find out, okay, with a high K dielectric, they need to use a metal gate. Now, it was not just a normal metal. They definitely added some more materials in it. And they added some more material in it because why? They wanted to have this gate kind of having the similar energy to be able to, for example, in NMOS case, have a good flow of electrons. So think of that. Okay, simple metal is not going to work. They added some more combination in it. What they call it, a work function. They added some material to change its work function, mean change its energy so that it can affect the same energy of electrons and in a similar way as if it was a polysilicon. Think of like that. So they make some other, that was Intel's secret. I don't know if it was still disclosed or not. I don't know. But definitely the papers on 45 nanometer, 30 nanometer, 32 nanometer, Intel doesn't disclose that publicly. Now the thing is, remember that when I said that traditional transistor have a polysilicon, N-type polysilicon for NMOS, P-type polysilicon for P-type. And when we found a metal gate, we had to do the exactly same thing. They had to add some material into it, some combination of separate multiple things, but still calling a metal gate. Okay, such that it favors more N-type poly and kind of similar characters as P-type poly for PMOS case. And that's where the discussion of that word function and all that came. And okay, now we had finally a kind of combination that they tested in the lab and they tested in a test chip, and finally things were working. And next thing was, okay, go to production. I think I already mentioned the properties of this new combination. Okay, those vibrations were kind of minimized. Also, there was a good bonding here. There was another problem they found when there was a polysilicon. If there's a high K, there was charge trapping on this surface. And with this one metal and this one, this became really smooth, like one atomic layer smooth. Yeah, okay. And then with this combination, the transistor VT threshold, the current flow and all that was in a similar line as the regular kind of Intel scaling was going on. Okay, I still have a lot more material. I think I need to do another video on this one. So that's it for now. Hope you found it interesting and learned something new. See you in part 2 of 45 and 32 nanometer in the next video. Thanks so much. Bye.